Welcome to this explainer. I am absolutely thrilled you're here with us today because we are going to dive into how the very definition of global power has radically shifted right beneath our feet. We're looking at this totally fascinating shift. It's not a race with a simple finish line, you know? It's more of a high-stakes competition to literally shape the rules of the next industrial era. We are talking about a fundamental reimagining of what makes a nation truly powerful in the 21st century.
Think about it. For most of human history, global power was actually pretty straightforward. It came from controlling land. You build an empire, you expand your borders, and bam, you were powerful. Then, as navigation improved, well, it evolved into controlling the oceans and global trade routes. Fast forward to the 20th century, and geopolitical dominance was all about controlling oil and natural gas. But today, this evolution has brought us to something far more complex. It's this modern race for cutting-edge technologies, massive factories, critical minerals, and the incredibly complex infrastructure that actually makes the entire energy transition possible. The countries that master this new domain, they aren't just going to be wealthy. They are going to dictate the geopolitical reality for the next 100 years.
So here is our game plan for today. We're going to peel this topic like an onion. We'll start with part one, the macro view, then move to the big three global players, dig into the underground layer, explore engineering as geopolitics, and finally, we'll zoom all the way down to a microscopic question.
All right, let's kick things off with section one, the macro view, and look at how building a comprehensive ecosystem changes, well, literally everything.
You know, when most people think about China's incredible rise, they usually picture enormous factories, endless rows of shipping containers, and low-cost manufacturing. But honestly, that is only a fraction of the story. China didn't just become the factory of the world by accident. As their economy expanded, they purposefully built a comprehensive, vertically integrated industrial ecosystem. They invested heavily and strategically across the entire chain. We're talking everything from securing mining partnerships in developing nations and mastering material processing, all the way to advanced research, infrastructure, and export logistics. Take something incredibly complex, like an electrolyzer. That's the machine that splits water into hydrogen and oxygen. Building just one of those requires advanced materials, precision manufacturing, highly specialized catalysts, and sophisticated control software. None of that just magically appears overnight. It requires years of relentless investment, a massive network of suppliers, and a mature industrial base where every single piece of the puzzle is already in place. So what's the true driving force giving China that mature industrial base? It's a fundamental economic principle we call the economy of scale. It's pretty simple. As production grows, the cost per unit falls. This happens because those massive fixed costs, like, say, building a billion-dollar factory, are spread out over more and more products. But even more importantly, manufacturers actually gain incredibly valuable experience improving their processes as they go. They learn how to reduce waste, how to speed up assembly, and how to optimize their supply chains. This very principle has been the engine driving down the cost of technologies we see every single day, like solar panels and electric vehicle batteries, taking them from expensive, niche products to everyday global commodities.
To really visualize that scale in the real world, just picture two companies making the exact same complex product. One builds 100 units a year, and the other builds 100,000. Who do you think learns faster? Who uncovers the most efficient manufacturing shortcuts? Who reduces their error rate quicker? And who has the leverage to aggressively negotiate better prices from their raw material suppliers? The company building 100,000, for sure. Scale doesn't guarantee leadership forever, but it rapidly drops costs and creates a massive barrier to entry. It makes catching up nearly impossible for anyone trying to start from scratch.
Knowing how hard it is to catch up to that massive scale, let's jump right into section 2, the big three, and see how Europe and the United States have entered this race with entirely different game plans. Look, neither Europe nor the United States is trying to just copy-paste China's strategy. They know they can't match that exact ecosystem overnight, so instead, they're leaning hard into their own unique historic strengths. Europe leverages advanced engineering, high-value manufacturing, and an incredible ability to coordinate across diverse, specialized countries. You've got Germany developing heavy industrial tech, Denmark expanding vast networks of offshore wind, Spain leveraging its endless sunshine for solar, Norway contributing steady hydropower, and France bringing robust nuclear energy to the table. It is one massive, interconnected market. But as with any large bureaucracy, broad coordination can, significantly slow down decision-making.
Now, across the Atlantic, the United States relies heavily on financial incentives rather than top-down coordination. They use targeted tax credits, massive federal research funding, and their world-class risk-tolerant venture capital ecosystem. The U.S. also leans on its deep expertise in software and artificial intelligence. They're betting that the future energy system will be defined just as much by how efficiently hardware is operated by software as by the hardware itself. So this sets up a totally fascinating head-to-head-to-head competition among three major economic powers. China focuses on absolute industrial scale and supply chain dominance. Europe emphasizes coordinated infrastructure and cross-border engineering integration. And the United States leans heavily into disruptive innovation, private investment, and financial incentives to spur rapid growth. Each of these models has distinct strengths that have propelled them forward, but each also has very clear, potentially crippling vulnerabilities. And as this transition accelerates, there is absolutely no guarantee of who is going to dominate this next era.
But if we peel back the visible layer of those massive factories, policies, and economic models, we hit Section 3, the underground layer. This is the invisible mineral battle.
If gigafactories and wind farms are the highly visible part of this competition, minerals like copper, nickel, lithium, graphite, rare earth elements, platinum, and iridium, they are the invisible foundation. Without this specific critical list of raw materials, modern energy technologies simply cannot be built. I mean, you can't wire a smart grid without copper, and you definitely can't build a high-capacity electric vehicle battery without lithium and nickel. But here is something truly surprising that fundamentally shifts how we should think about all this. Actually finding and mining these minerals from the earth? That isn't actually the hardest part of the equation. No way.
This raises a brilliant question from our sources to illustrate a massive vulnerability. Imagine discovering a massive, highly lucrative gold mine right within your own borders. It seems like an incredible win, right? But if every single refinery capable of processing that raw ore into actual usable gold bars is located on another continent, who really controls the value of that resource? This perfectly highlights that complex supply chains and advanced refining capabilities matter just as much, if not far more, than simply possessing the natural resources in the ground.
Let's look at how that actually plays out across the strategic value chain. Digging the rock out of the ground, mining, is literally just step one. The significantly bigger, way more complex challenge is step two, processing and refining those raw, often toxic materials into a highly pure form that manufacturers can actually use. As you move from refining to manufacturing the components, to engineering the final product, and finally to global distribution, every single stage adds immense economic value. And more importantly for global powers, every single stage creates strategic leverage for the country that controls it. Basically, if you control the refining bottleneck, you control the entire industry downstream.
And that brings us to Section 4, Engineering as Geopolitics, and the massive ripple effect of these technological choices.
To truly grasp the sheer mind-boggling scale of the engineering we are talking about in this new era, just consider this one fun fact. A single modern offshore wind turbine can stand over 250 meters tall. That is taller than many famous skyscrapers. The massive blades are so incredibly long that just one rotation can sweep an area larger than an entire football field. And we aren't just building one of these, nations are planning to deploy thousands of them out in the unforgiving ocean.
Because of this staggering, completely unprecedented scale, engineering just doesn't happen in isolation anymore. It triggers a massive domino effect. A single decision made by a material scientist in a lab influences exactly how a component must be manufactured. That specific manufacturing capacity then dictates the flow of global trade. Those trade flows directly influence international diplomacy and alliances. Diplomacy dictates national security priorities, and ultimately, national security shapes a country's entire global strategy. In this new paradigm, every design choice, every new supply chain bottleneck, and every factory breaking ground has massive, far-reaching geopolitical consequences.
Which leads us to our final stop, Section 5, the microscopic question, where we enter the engineering to try and figure out what actually scales.
Around the world, it isn't just governments and policymakers watching this high-stakes global chess match. Major investors and financial institutions are paying very, very close attention too. They're looking at massive concepts like hydrogen, artificial intelligence, digital twins, critical minerals, enormous automated factories, and sprawling intercontinental pipelines. History tells us that major industrial transitions always involve wild experimentation. Inevitably, some ambitious projects will succeed, while many others are going to fail. All of these concepts, they're distinct pieces of the exact same puzzle driving this historic transition. They are all fiercely competing to be the foundational infrastructure that actually survives the decade.
And that leaves us with this final, incredibly provocative question. As we zoom all the way down from global superpowers wrestling for dominance right into a microscopic fuel cell catalyst, we really have to ask, can hydrogen actually deliver on its enormous promise, or is it just generating all this excitement without actually changing the world? To answer that, we have to leave the high-level politics behind and deeply enter the engineering. Because inside a single molecule of hydrogen, inside a tiny, silent fuel cell, the entire future of the global energy transition might already be taking shape. Thanks so much for joining us for this explainer. We'll catch you next time.